Final test for improper integrals, one final theorem, a comparison test. So suppose that we have two different functions, continuous functions, with the property that f of x is always greater than or equal to g of x, and both of them are non-negative, and we're assuming that this is true for all x greater than or equal to some cutoff value. And so take a look at what this says. If the integral from a to infinity of f of x converges, then so does the integral from a to infinity of g of x also converges. And vice versa, if the integral from a to infinity of g of x diverges, then the integral from a to infinity of f of x dx also diverges. What's going on here? If we have, so note here, f of x is always greater than or equal to g of x. So in this first case, g of x is smaller. G of x is smaller than something that converges, so it's also going to converge. In the other case, g of x diverges, f of x is bigger. Sorry, I shouldn't say g of x diverges. The integral of g of x diverges. F of x is bigger than that, bigger than g of x, so it also diverges. So this should make some intuitive sense. If you're bigger than something that diverges, you're also going to diverge. In this case, everything is non-negative, so we're only thinking about going off to plus infinity. If you're bigger than something that's going off to plus infinity, you're also going off to plus infinity. In the second case, if you're smaller than something that's positive, smaller than something that's finite, and you're finite and non-negative, you're also going to converge. So this should all make some intuitive sense here. And also I should say that the comparison test is also valid for improper integrals of other types. So those are the types where we have a finite interval but an unbounded function, stuff like that. And so this theorem is going to allow us to determine the convergence or divergence of some integrals that we wouldn't otherwise be able to do. Sometimes because we simply can't evaluate find a antiderivative. So as a first example of this, let's take a look at the integral from 1 to infinity of 1 over the square root of x cubed plus 1. And so if we were doing this using previous methods, our first job would be to try to find an antiderivative of 1 over the square root of x cubed plus 1. And that's going to be a very difficult problem. I don't know how you come up with an antiderivative of 1 over x cubed plus 1. The square root of x cubed plus 1. And so we don't want to do this by finding antiderivative. We want to compare. Remember, this is called the comparison test. We want to compare this to something that we can determine the convergence of. And so what we want to do is realize that this looks kind of like the square root of x cubed plus 1. It's kind of like the square root of x cubed, which would be x to the 3/2. So realize the following. X cubed plus 1 is bigger than x cubed. So the square root of x cubed plus 1 is bigger than the square root of x cubed. And so then if we take the reciprocals of each of these, that changes the direction of the inequality. So what we have is that the integrand is less than or equal to 1 over the square root of x cubed. And this is just x to the 3/2. So what do we, and also it's worth noting here that that's never 0. And what do we know from our previous work here? Our previous theorem, the p integral over the interval a to infinity. Well, here, this is exactly the situation that we have. That's exactly the situation that we have here. So if P is 3/2, it converges. So from previous work, our P integral theorem, the integral from 1 to infinity of 1 over x to the 3/2 dx converges. We could go back to that sheet of paper to figure out exactly what value it has, but the exact value isn't important here. The important fact is simply that it converges. So the integral of our bigger function converges, and so we can conclude, so by the comparison test, this actually does converge. So what's the summary here? We couldn't do this antiderivative. That's too tricky. We couldn't do this antiderivative because it's too tricky, so we compare it to something that we can find the antiderivative of, and we can determine that it converges. And because our integrand is smaller than the integrand here, and this integral converges, this integral converges as well. Now, we don't know what the value is. We don't have an estimate right now. I mean, we could estimate it with our previous value, but it's okay. We just know that this has to converge. Okay, let's do a paired example here. Determine whether the integral from 5 to infinity of 1 over x cubed minus 1, all of that to the 1/4 converges. So again, let's think this whole thing looks kind of like x to the 3 over 4. You know, we get rid of that minus 1. That's just, the denominator is just x to the 3 over 4. We observe that x cubed minus 1 is less than x cubed. And if we take the 4th root of that, that's still true. And if we take the reciprocals, just as before, oops, I forgot the 1/4 there. Just as before, taking reciprocals is going to change the direction of our inequality. Okay, so what do we end up here? We want to think about integral from 5 to infinity of 1 over x to the 3/4 dx. And going back to our previous theorem here, we can see that P is 3/4, so we're in the diverging case. And because our integrand is always bigger than the integrand here, and it's never negative, we can determine that this doesn't converge, this diverges. So once again, we are using this test to help simplify things. We would have a very difficult time finding the antiderivative, but if all we care about is determining convergence or divergence, we can do that very easily.